Understanding linear motion is a fundamental concept in physics. It describes the movement of an object along a straight line. Imagine a car driving down a straight road. That car is in linear motion. Now picture a ball thrown straight up. That ball is also exhibiting linear motion. In both cases, the object's path is a straight line. Linear motion doesn't have to be at a constant speed. The car could be accelerating, and the ball will slow down as it goes up and speeds up as it comes down. What matters is that the direction of motion remains along the same straight line. This type of motion is the simplest to analyze. It forms the basis for understanding more complex movements. Linear motion is all around us. Think about a train traveling on its tracks. That train is a great example of linear motion. The tracks provide a straight path for the train to follow. Now visualize a bowling ball rolling down the lane. It's also moving in a straight line. Linear motion is not limited to large objects like trains and bowling balls. Even something as small as a grain of sand, dropped from your hand, is experiencing linear motion as it falls to the ground. These everyday examples highlight the prevalence of linear motion in our world. Understanding this simple type of motion helps us comprehend the movement of many objects in our surroundings. Let's imagine a block placed on an inclined surface. This inclined surface could be anything from a simple ramp to a hill. The block is at rest due to friction. Friction is the force that resists the relative motion of the block against the surface. If we give it a gentle push, it starts to move down the incline. This push overcomes the static friction holding the block in place. This simple scenario is a classic example of linear motion. Linear motion refers to the movement of an object along a straight path. The block moves in a straight line down the slope. This straight line motion is influenced by the angle of the incline and the force applied. We can analyze this motion using the laws of physics. These laws help us understand the forces acting on the block and predict its behavior. The force of gravity pulls the block downwards. Gravity is a constant force that acts on all objects with mass. However, the incline prevents the block from falling straight down. The angle of the incline changes the direction of the gravitational force. Instead, the block slides down the slope. This sliding motion is a result of the gravitational force being split into components. We can break down the force of gravity into two components. These components help us understand how the block moves on the incline. One component acts parallel to the incline, pulling the block downwards. This parallel component is responsible for the block's sliding motion. The other component acts perpendicular to the incline. This perpendicular component pushes the block against the surface of the incline. This perpendicular component is balanced by the normal force from the incline. The normal force is the reaction force exerted by the surface to support the block. Newton's second law of motion is fundamental to understanding linear motion. It forms the cornerstone of classical mechanics and is essential for analyzing how objects move. This law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. In mathematical terms, it is often expressed as F = ma, where F is the net force, m is the mass, and a is the acceleration. In simpler terms, a larger force produces a larger acceleration, and a heavier object accelerates less under the same force. This relationship helps us understand why pushing a car requires more effort than pushing a bicycle. In our block on an incline example, the net force acting on the block is the component of gravity pulling it down the slope minus the force of friction. This scenario is a classic illustration of Newton's second law in action. This net force causes the block to accelerate. The steeper the incline, the greater the component of gravitational force acting along the slope, and thus, the greater the acceleration. By knowing the mass of the block and the angle of the incline, we can calculate the block's acceleration using Newton's second law. This calculation is crucial for engineers and scientists who design systems involving motion. This powerful law helps us predict the motion of objects under various forces. Whether it's a spacecraft navigating through space or a car accelerating on a highway, Newton's second law provides the framework to understand and predict their behavior. Section 5. Forces that change. The spring force. So far, we've considered situations where the forces involved are constant. But what happens when forces change? Let's consider the force exerted by a spring. The more you stretch or compress a spring, the greater the force it exerts. This force is proportional to the displacement from the spring's resting position. This relationship is known as Hooke's law. It describes the behavior of ideal springs. In reality, springs may not always follow Hooke's law perfectly, especially at large displacements. However, it provides a good approximation for many real-world scenarios. Understanding how forces change is crucial for analyzing more complex motions. Section 6. Block and a spring. An example of varying force. Imagine attaching a block to a spring. We pull the block, stretching the spring. When we release the block, it starts to oscillate back and forth. This oscillation is driven by the changing force of the spring. As the block moves towards the spring's resting position, the spring force decreases. As the block moves past the resting position, compressing the spring, the force increases again, pulling the block back. This back and forth motion is an example of simple harmonic motion. It's a fundamental type of motion found in many systems, from pendulums to vibrating molecules. Analyzing this motion requires considering the continuously changing force of the spring. Calculus provides the tools to handle such situations. Section 7. Falling with drag air resistance matters. When an object falls freely under gravity, we often neglect air resistance. However, in reality, air resistance plays a significant role, especially for light objects or objects falling from great heights. Air resistance, also known as drag, is a force that opposes the motion of an object through the air. The faster the object moves, the greater the drag force. This drag force depends on the object's shape, size, and speed, as well as the properties of the air. For a given object and air conditions, the drag force is generally proportional to the square of the object's velocity. This means that as the object falls faster, the drag force increases rapidly. Section 8. Terminal velocity. Reaching a constant speed. As an object falls through the air, its speed increases. Consequently, the drag force acting on it also increases. Eventually, the drag force becomes equal in magnitude to the force of gravity pulling the object down. When this happens, the net force on the object becomes zero. According to Newton's first law of motion, an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Since the net force on the falling object is now zero, it no longer accelerates. It continues to fall at a constant speed called the terminal velocity. Section 9. The importance of understanding linear motion. Linear motion, despite its apparent simplicity, is a fundamental concept in physics. It forms the basis for understanding how objects move in a straight line, which is crucial for many scientific and engineering applications. It helps us describe and predict the motion of objects in a wide range of scenarios. Whether it's a ball rolling on a flat surface or a spacecraft traveling through space, linear motion principles apply. From understanding the motion of cars and trains to analyzing the fall of a raindrop, the principles of linear motion are constantly at play. These principles allow us to design safer vehicles, optimize travel routes, and even predict weather patterns. Moreover, linear motion serves as a stepping stone to understanding more complex types of motion. In physics classes, students first learn about linear motion before moving on to more intricate topics like circular motion and oscillations. By understanding how objects move in a straight line, we can build upon that knowledge to analyze motion in 2 or 3 dimensions, rotational motion, and even the motion of waves. This foundational knowledge is crucial for fields such as engineering, robotics, and environmental science. Therefore, a firm grasp of linear motion is essential for anyone seeking a deeper understanding of the physical world around us. Whether you're a student, a scientist, or simply curious about how things work, Mastering linear motion opens the door to a deeper appreciation of the universe's complexities.